All right, I think we are live. Hello, hello, everyone. Welcome to another DataStax live stream. Before we jump into it, let's make sure that everybody's here and present in the chat. Can we get a sound off of everybody and where they are from? I'm from the Bay Area specifically. Annie and Andy's over here as well, if they wanted to share.
I'm currently based in Phoenix, Arizona, so definitely still a little warm over here.
Awesome, awesome.
Hey everyone, I'm from Chicago. I saw someone else was from Chicago earlier, a few days ago. Prashant, if you're back, we're in the same city.
Nice. Yeah, we got a good. We're all kind of scattered here, us hosts, but I see so many different places here in the chat. We got Toronto, we got Raleigh, we got New York. I love New York. I was just there a few weeks ago. We got LA, we have Seattle. Ooh, we have Norway.
Wow.
KM. Nice to meet you. Oh, Phoenix. Robert's in Phoenix.
Okay, fellow
Sweet.
Arizonian.
We have Munich, we have Poland, we have another Seattle. Awesome, awesome. Well, nice to meet you all. We are super excited for today's session. I'm gonna go ahead and put up my slides. Let's go. All right. So I hope you've seen the title already if you've registered for this live stream. It is Gen AI 101, getting started with a vector database. So we have you for the next hour here to tell you about how to get started with the vector database. Specifically, we're going to lay a lot of foundations with some of these concepts, and then we'll actually get you a bit hands-on at the end and do a demo for you all. So what I hope that you get out of this next hour is you'll come out feeling very confident about getting started with the vector database and implementing it for your GenAI applications. So hopefully you get out of that's what you get out of this live stream today. But before we jump into that, let's formally meet your hosts. My name is Melissa Herrera. I'm a developer relations engineer here at DataStax. Super excited to be here today. I'm handing it off to your next host today.
Hi everyone, my name's Annie Fan. I'm a lead solutions engineer at DataStax, as mentioned, based in Chicago, and I worked really closely with Melissa and Andy. Really excited to work with both of them and to do this live stream today. Go ahead, Andy.
Thanks, Annie. Hey, everyone. I'm Andy from Phoenix, Arizona, and I'm stoked to be here with you all for a pretty fun and exciting live stream. And so let's get into it.
Awesome. Yes. And I know it might be a surprise seeing Annie and Andy on here. They will be my co-hosts as mentioned. So they'll be here monitoring the chat, answering your questions, and then just having a conversation with us today and to help talk about getting started with the vector database and also tell you all about different concepts that we'll be learning. So let's go into the agenda. So we will first be talking about vectors and the importance of that in generative AI. So again, laying the foundation there and how we can represent our data with vectors. And then we'll be talking about embeddings. So what's the difference between vectors and embeddings? Are they the same? Are they different? And then how these apply to vector databases. So then we'll introduce to you what a vector database is. We'll talk a little bit about similarity search with vector databases, and then an overview of Astra DB, which is DataStax's vector database. And then we'll actually get started with the vector database to end it off, and we'll be doing a hands-on quick start example. This isn't necessarily a workshop, but I will be doing a demo, which you could follow along with the docs, and you'll see that as we go through the live stream. So a lot of fun stuff planned for you all today. And again, it'll be myself, Annie, and Andy helping you all along the way understand these concepts. So please feel free to ask some questions in the comment section or in the Q&A section as we go on. Oh, and a fun little tidbit. And please stay until the end. We have a quiz for you all, and the winner of this quiz will get some free swag. So there will be one winner, but you have to stay all the way until the end so that you can take the quiz. And the quiz will be based off of content that we'll be sharing today. So yeah, please stay through and through. All right. Everybody loves some swag, right? You guys sound off in the comments. If you want some swag, give me a thumbs up, and we'll be happy to have you till the end. All right, we have RAG. Everybody know what RAG is? Can I have some interaction in the comments? Do we know what RAG is? Can we define RAG? Are we familiar with it? I'll give you all a minute. Who's heard of RAG? Juan says yes. Who can define RAG for me? Awesome, Venkat. Retrieval-Augmented Generation. Ken, Retrieval-Augmented Generation. Awesome, cool. We have a great idea of RAG, but a quick disclaimer. This live stream is not RAG focused. We will be mentioning RAG to kind of help with the ideas here today and saying how they relate to a vector database. But this is not the main focus. Our main focus is getting you started with the vector database. However, just wanted to call that out so that in case we do mention it, you understand how they kind of play a part with each other. I do want to call out, though, that DataStax has a ton of resources that do focus on RAG. So please feel free to look at those. We have a ton of live streams that talk about RAG as well. But today's session, we are focusing on vector databases. All right. So quick introduction. What is generative AI? So just to lay some groundwork here, and I hope we're all pretty familiar, but if you're not, just a quick 2-minute briefer. Generative AI is a class of AI, artificial intelligence, which is basically just the training of large data sets over a large period of time to identify patterns within your data and use that within your applications. So essentially what generative AI is different from regular AI is that now you are generating new content based on the data that you've trained it on and the patterns that you've identified. So a really great example here of describing and seeing what generative AI is ChatGPT. So we're all familiar with ChatGPT. And if I were to ask ChatGPT a question such as what is generative AI, then we might notice it give us this pretty concrete definition of what it is. And I can also get this definition and ask this question in another search engine. So if I were to do a Google search or any other search engine that you might use, we might get a concrete definition just like we're seeing here. And notice that it has a pretty formal tone, pretty textbook. So how does this make it generative AI using ChatGPT? What if I were to do a follow-up question such as, now explain that to me like you would do to a 5-year-old? And if I were to give this query to a typical search engine, it might not know how to respond to this necessarily. It might just give me a response that is based off of the keywords from that question alone, but it won't be able to reference a previous question. It won't be able to kind of generate a new response to me as I'm asking it in that query, right? I'm asking it to explain it to me like you would to a 5-year-old. But ChatGPT is able to do that. So we could see this question here. Generative AI is like a smart robot that can make new things. If you tell it a story idea, it'll write a whole story for you, et cetera, et cetera. So now we can kind of get this new content based on what I've asked it that won't necessarily been a tip. So we talked about before we cut off what generative AI is and what kind of applications that we can build, and how generative AI creates new content based off of huge amounts of data. So the challenge with generative AI is, since we have all of these huge amounts of data, and this data could be large amounts of text, images, audio, video, and even unstructured data, so talking about PDFs or PowerPoints, is if we want to make some queries or do searches back into the data and use it for application, we're going to need some complex queries to do that. And we're familiar with traditional databases and what they're able to do for us, but for the amount of data and for the tasks that we need, specifically with the complex queries, traditional databases might not cut it. And the reason for this is because traditional databases struggle with a few things. So one of those, 3 of them are listed here. The first one being querying high dimensional and unstructured data. It struggles with that. And high dimensional data, we'll go into it a little bit later. It struggles with fast retrieval from these large data sets, as well as scaling efficiently as data grows. So what do we need that can do those things without struggling. We need something that will be able to handle all of the above, as well as be able to do those complex queries that we've mentioned. And when I say complex queries, I'm talking about finding similar documents or retrieving similar records. In a traditional database, we're familiar with doing things with kind of a structured syntax in like maybe a relational database, and it's all kind of based off of keywords or specific operators. So having the ability or flexibility, I might say, oh, find something a bit similar to this document that might have the same context as this, we need something to do that. So what can do that for us? It is a vector database. So we need this. And that's the whole focus of today's live stream. But what qualities of a vector database makes this so great for generative AI applications? All of these things. And just to break down a few, oh, we went back. So just to break down a few, it supports unstructured data really well. It efficiently stores our high dimensional data, so vectors. So it's in the name, vector databases and embeddings. And again, we'll go over the difference and the what those two things are. The complex queries, as you mentioned, just kind of skimming here. But the one important thing, or one of the main important things, is this last one here, allows for fast data access and retrieving relevant results. And that's where we kind of go back to our RAG applications. So in RAG applications, again, this is not a RAG focused tutorial, but we need a vector database to be able to handle this data that we can augment to our LLMs and our data sets to help with our generative AI applications and maintain relevancy in our results. How many times have you asked ChatGPT a question and it's given you kind of a irrelevant result or it's hallucinated? Annie and Andy, I'm sure you can both kind of relate or
Far
think
too many
about the time that
times.
you've done that.
Mhm.
Exactly, right? And that happens a lot with our with so much data sets that are only trained to a specific point. And to help fix those instances, you need a vector database. And oh, no more technical difficulties here. So what exactly though are vectors? Oh, we're flipping back and forth. Sorry, that's not me, guys. So what exactly are vectors? If we think quickly back into our math classes from before, maybe your 5th grade math class, we learned about these kind of line graphs and vector spaces. And we could tell by here, just real quick, we have a 1-dimensional space, a 2-dimensional space, and a 3-dimensional space. And going back to the definition that we used for vector in math class versus how I define it now, I think one common way that we can describe both terms or both contexts is that a vector is a term that refers to a quantity that cannot be expressed by a single number. So let's use this in the concept of a 2-dimensional space and representing our data. So let's take, for example, I want to represent this puppy. And I'm going to have my x-axis represent wild and domestic. Oh, we're going back and forth. And in the y-axis be feline versus canine. So if I want to represent this puppy here, maybe it'll be more on the domestic side and the canine side. And if we want to do a search query back into our vector space back then in math class, and we wanted to see how similar 2 points were to each other. So for example, if I introduce maybe a kitten, back then in math class, we would do what's called the distance formula and calculating the distance between these 2 points. Same idea goes for finding the similarity between these two in a vector space. So what does that mean when we introduce multiple points of data? Now we can kind of mentally group some of a group of data sets, data on this vector plane. So for example, on the top right, we have all of these kind of home domesticated dogs. On the bottom, we have kittens. But maybe on the left side, which kind of errs more on the wild side, we have a wolf, but it's still a canine. Or on the other side, it's a wild feline, a lion. So we can kind of see how this groups on a vector space. But if that's still not kind of making sense about how vectors represent our data, let's do a quick demo. So I will share my screen here. All right. Thank you, Amy. Thank you so much. All right. Here is Astra DB. It is our vector database, as I mentioned previously, and we are looking right now into a collection. So a collection is where you store your data. And I have actually the exact data points that you saw in that last slide. And again, we have our Labrador puppy, we have our tabby cat, et cetera, lion, and wolf. And I want to do a search query. Let's just use the German Shepherd, for example. So if I want to do something that's a bit similar to German Shepherd, we might suspect that we'll get the domesticated dogs. We might get the wolf before we ever get recommended the cat breeds or the feline breeds. Notice here how they're kind of out of order. And once I do the similarity search, which I can just do by pressing this button here, we can see how they reorder based on how similar they are to each other. So let's do a search on the German Shepherd and see
Hey,
how they reordered to show the German Shepherd as similarity score 1. Following that, as expected, we have the Labrador, the Corgi, and the Wolf, and then the feline breeds on the bottom. And notice how the lion has the least similarity to the German Shepherd. But again, this is only in a two-dimensional space. We're describing our data only with 2 dimensions, and that was wild versus domestic and feline versus canine. What if we kind of expanded further from just the two-dimensional space in describing our data? Let's hop back quickly
hey, Melissa, I
into
think a
our
really good
slide.
question came up in the chat from Rajan.
Yeah.
You mentioned, how did we get these numbers that were calculated for these animals over here?
Yeah, Rajan, great question. Um, these were all completely arbitrary vectors that we did. And that's just to kind of visualize what it would be on a two-dimensional space. And we're gonna kind of get to where or how we can actually represent the properties a bit deeper so it gives us a better description of the data points. That's a great question. So yeah, keep in mind the two-dimensional space can only go so far. And that's why we must think about n-dimensional spaces. What if we had many, many numbers within our vectors beyond just the two-dimensional space, beyond just describing them of wild versus domestic or canine versus feline? What if we were able to dive deeper than that and describe other properties, maybe their habitat, their lifespan, how big they are, how small they are, etc. And we get into this realm of embeddings. And I'll hand it over to Andy to talk a little bit more about that.
Thanks so much, Melissa. That was great. So I think we have a good understanding of what a vector is and what it, semantically means, but let's dive a little bit deeper and get more into embeddings and learn more about them. So let's get started. Um, so perfect. What is a embedding? How is it different than a vector? So on and so forth. Well, first off, vectors and embeddings are often used interchangeably. So definitely don't freak out if you hear them kind of being used for one another, because oftentimes you will hear a vector and or an embedding in the same context. And that usually means that both of them are referring to the numerical representation of a piece of data. And that's exactly what you've been seeing in our demo with all the different animals here on the left-hand side. But if we want to get a little bit more specific or a little bit nuanced, well, an embedding is actually a more of a technique to actually represent a piece of data via a vector. And so, although what you see here on the left-hand side is just arbitrary numbers, embeddings are what we actually hold the semantic meaning through this array of numbers, aka vectors. And so that's great. The key difference is that embeddings are designed to capture two main things. First off, the semantic relationship and the contextual characteristics of a piece of data. And so we go far beyond just canine and feline, but now we characterize all the different aspects of a piece of data. And here you see just a quick image of different items and data points that are characterized in the 300 dimensional space. So you can see chicken, wolf, so on and so forth. We can characterize this through embeddings. So what does an actual embedding really look like? Well, an embedding really is far more intense than these examples that we're showing you. This is an example of a real life vector embedding of a computer terminal. And so what we see here is not just 2 dimensions or 2D, but in fact, actually 1536 dimensions. And luckily for us, it's very easy to generate these vectors, and these embeddings through embedding models. And so in this case, we actually generated this vector embedding through OpenAI's text embedding ADA002 model, which then outputs this vector that you see here. And so this is a one-to-one match between our computer terminal and our embedding. And so that's kind of where how I like to think about it is all embeddings are vectors, but not all vectors are embeddings. So that's kind of one
Yeah.
way I like to frame it.
Hey, Andy, great explanation. And I just wanted to call out Rajan's question from earlier that you actually answered through your explanation real quick. So yeah, just to hone in again, like he's asking how do these vectors even get calculated, right? And so Andy talked a little bit about OpenAI's embedding model. But yeah, embedding models are how we do this. And just depending on your use case, you might use a specific embedding model. So there are a lot out there from different providers that are able to do this across different dimensional spaces. So this one in particular is 1536, but others might be even larger. Some might double that, just depending on how granular you want to get with your data. Andy, I don't know if you want to add to that.
No, you're exactly right there. Also, keep in mind that the more dimensions, the more specificity you're kind of defining your data as. And so the less dimensions, you're kind of keeping it more generic, the more obviously you're holding more of these characteristics or properties and attributes. So something to keep in mind while you're doing your vector searches and looking at embedding models. Um, but yeah, great question. And so awesome. We learned about vectors. We've seen a quick little demo, and now we learned about embeddings. But how do we find the similarities between these embeddings, and how is that really useful? This is where we actually come into a new term called vector search. And with that being said, I'll pass it over to Annie to kind of give a little bit more in-depth overview of vector search and its importance.
Great, thanks, Andy. I think one other point that I kind of want to make about like embeddings and how the values are created. Um, like these embedding models are kind of like a new wave of AI and ML. There are still traditional ML techniques where you can say like, I want to
Mhm.
define this number of parameters and I want to use this model to assign them based on like XYZ, and all of that can be like still done. But the power of embeddings models is that like someone else has created this extremely powerful model that abstracts away all of that sort of decision making in a way that's like really reliable and powerful. So it's still ML. You're just like assigning weights to different things. But whether you're kind of defining that yourself or allowing like providers such as OpenAI and Vertex AI and all of these other companies who've trained vast amounts of data to do that, that's like kind of the major difference there. Just to kind of
That's
expand a little more.
Mhm.
that's a really good point, Annie. And adding on that, kind of going off of depending on what use case you use, you might test across multiple embeddings models and determine how well they're doing for your use case based on how deep the similarity search is. So if you saw in the example, we had German Shepherd ranked number 1, and you saw the similarity score of 1, and then you saw how the others ranked under it, right? So depending on how your data was embedded, one might calculate all the canine breeds as the most similar. And then maybe on one, you might get the lion more similar to the wolf, just based on how it's weighted domestic versus wild or canine versus feline. So it really all depends. And you can use all of these embedding models pretty much with the single API call to be able to do that. We'll kind of talk a little bit about more how it's in Astra DB, but that was a great call out, Annie. So thank you. Oh, we do have some
Sure.
questions here. Um, let's see. Steve, how does a model assign a vector to a flat panel display so that it appears as similar to the CRT monitor shown in the example? Can you expand on that question a bit more, Steve?
I think I kind of know what he's getting at here. So if a model was given like flat panel display, how is it assigned something so that if you were to do a vector search that you'd get
Got
that
it.
as a
Yeah.
similar result? Um, if you wanted to go ahead and answer that.
Got it. Yeah. So Steve, so maybe the visual part of it won't be the only thing that it's being characterized on, right? So it'll still have the context that these are both computers, and then it'll grab properties from the fact that they're both computers and also include that in the embedding. But to your question, maybe you'll see more this flat panel displays as ranked higher similarity versus the older monitors, and then those will have like kind of less. But contextually, they're still ranked maybe the same based on the fact that they're both computers. I hope that makes sense. Another question, and also Annie, did you want to add to that?
Yeah, I think like the way the vector itself is assigned is like the model that you're using is trained on a ton of natural language and text data. And then based on all of that training, the model has a way to kind of represent the flat panel display as like this large array of numbers that are created based on that foundation of huge amounts of data. So however, that's like generated through the embeddings model, that's like a bit abstract. The numbers themselves, like it's hard to know what they mean, but like when paired with the model, it represents like this is a screen that's used for like viewing like XYZ, you can connect it to blah, blah, blah. All of that is like represented somehow in the vector. And so that's how, like, once that representation's created, that's how you're allowed to do those similarity searches and have those two items be kind of related through that model. There's a ton of questions coming up. Let's keep going.
Yeah,
Yeah.
hopefully your answers hopefully your questions get answered through this next part with Annie's explanation.
Cool. Okay, so let's talk a little bit about vector search, which is interchangeably called similarity search. So something that you'll need in order to conduct this similarity search or vector search is a vector database. So let's revisit some of the slides from the beginning of the live stream. Sorry, Melissa, are you able to do the slides for me? I think we were maybe both doing them. Great. Cool. So Melissa talked earlier about a traditional DB versus a vector DB. Traditional databases such as relational, old Cassandra, for example, they're really good at storing highly structured data. You can define different columns and query based on keyword search or operators, such as Melissa mentioned. But they struggle with querying these high dimensional vectors and unstructured data. They also struggle with retrieving this type of information from a large data set and scaling efficiently as data grows. But a vector database will allow you to find data that's similar to XYZ. So once you've taken your unstructured data and created vectors out of it, you need to put it into a vector database so that you can do those similarity queries. Next slide. So again, these are the qualities of a vector DB that are important for GenAI projects. A few that we want to highlight specifically in the next slide are one, we want a vector DB to be able to efficiently store high dimensional data. So vectors or embeddings, like these things that are being created by these powerful models. We also want the vector database to be able to support high performance searches using approximate nearest neighbor algorithms. So when we're trying to search for related vectors, related data within the DB, we need some sort of algorithm in place to make that efficient and quick and also accurate. Instead of doing like a scan of every single vector in the entire DB, we need something implemented so that you can pull only the most relevant in an efficient way. And then that's also related to the third point, which is allowing for fast data access and retrieving relevant results. One example of a vector DB is DataStax Astra DB. DataStax is the org that we work for. And a few of the algorithms available within it are cosine similarity, dot product, similarity, and Euclidean distance. These are all different metrics that you could use for calculating the distance and conducting your similarity search. If you want to go to the vector search visual, Back a few slides. Here at this one. So if we bring it back to this visualization, this is kind of what it's a visualization of what your data would look like after it's been placed in a vector DB. And so every data point is stored in a vector DB as embeddings. From there, you can run vector search queries to find similar points based on those embeddings using semantic similarity or proximity. And then vector search, if you implemented this with Astra DB, you can make these vector-based searches in real time. A few points about Astra DB. It's really quite easy to embed your data with Astra. You could either bring your own vectors or use the vectorized integration to create embeddings as you're uploading your unstructured data. There's a variety of easy ways to connect to your database from your application. So there are tons of different clients and drivers available. There's a really simple API, the data API, which you could use. In Astra, using all of those different connection methods, it's easy to store your data in the database. If you want to include additional fields beyond just the vector and the text itself, it's really flexible and you can store different data types as well. And then if you want to perform both complex and simple vector searches or just traditional searches that don't use vector similarity, all of that's possible using hybrid search via the UI, using our APIs, using the clients, using the drivers, kind of whatever method you want to do. So that's kind of why Astra DB is a pretty powerful option in terms of a vector DB. Cool. So that's kind of an overview of like what is a vector DB, why we need it. Moving, let me see. So up until this point, we've discussed vectors, vector embeddings, vector search, and vector DBs, all kind of in general. Maybe we want to address one or two of these questions before we go to the demo, which in a second, Melissa can get into showing the UI and showing how we do it with code. So anything we want to address from the Q&A?
Yeah, we can start up from the top. So one question that I see right here is how much does the embedding actually impact a model's response? Um, And so just to kind of shed a little bit of light into that, your model and your embedding model is very important because that's how your data is going to be characterized and classified. So that kind of digs into a little bit what I was talking about regarding the number of dimensions. Obviously, the more dimensions that your embedding model returns back to you means that it's kind of characterizing the data in a more fine-grained way. However, there's always this balancing act that you want to do where how many dimensions is too many, right? We don't want to do any, searches that are, across, millions and millions of vectors or dimensions long. And so usually, once you find this balancing act, we see that, anywhere from around 700 to 15, 26, even a little bit beyond that is kind of what the status quo is. And then obviously, like Amy mentioned, there's multiple of these third party, you know, companies that have come out with their own embedding models. So it's definitely something that you do not need to set up right out of the box. Don't know if anyone else wanted to shed some more light into that.
No, that was awesome, Andy. And just for the concept of time, we will go into the demo just really quick because I did promise that we're going to show you how to get started with AstraDB or a vector database in general. But thank you so much for the questions, and we'll be happy to follow up with these after if you'd like to keep in contact with us. But anyway, let's quickly do the demo, and we also have the quiz at the end. So I just wanted to show a little bit more of AstraDB to you all and how you can get started with a vector database in particular. Creating a database is really simple in our platform. All you have to do is go down to where it says create a database and give it a name, and then select your region and literally create database. You are on your way. It does take us a few minutes just to start up. So I will go into one of our existing databases that I already have and go back into our collection. Adding data is as simple as Annie was mentioning, which is just pressing our load data right here. And you can select a file. Let's see. Actually, let's go ahead and create a new collection. And then selecting the embedding generation method. Annie mentioned that we have a keyword called vectorize, in which you can bring in an external embedding source and then use that in your vectorization process. So it does it for you just in one go on insertion. And you can select the model that does well for you. You see the dimensions here. In the example, we used ADA. Here it is as well. And again, as Annie was mentioning, we have the similarity metrics built into Astra DB also, and you can select that based on your preference. Once that's done, go ahead and see, you can see that it's creating the collection. This only takes a few seconds, and then uploading your data is really simple as well. You just have to load your data, drag the file that you use. So in this case, we will go into our new collection. And I actually have a kind of more fleshed out CSV file for our canine and feline breeds. Let's do that this way. Here we go. And perhaps the demo gods aren't on our side right now for this. Let's try. There we go. And then on the top, it says field to vectorize. And again, that just means generating the embeddings. And we can select which column of our data that we want to turn into the vector. So this is where it's going to be grabbing the context from, turning it into that large string of numbers or an embedding. And this is what it'll be performing the similarity search based off of. In this case, I will do it off of the description column. And then once you click load data, in the background, it's doing all of the work pretty much for you and then creating the collection based off of which column you've selected to vectorize and then the rest of the columns that are there present. What you should see at the end there is all your data then loaded into your collection. And then you can see that a new column has been created called vector. I'll go into this JSON view right here. And it creates large dimensional vector for you based off of the description. And it actually updates the description column to the word vectorize. And that's just how you know that this is the field that is being vectorized and converted into the vector. And for all my people who like to do it through code, again, this was just through the UI. It's showing how easy it is to get started that way. But I know we're here because we like to develop and we like to get hands-on code. We also have that available too within our quick start guide, which I'll have linked as well. This will allow you to connect to your database via code. I personally use Python, but in our docs, we have ready Python as well as TypeScript and Java for you. In our code, once again, sorry for all the screen flipping, but in our code, we will have here on the initialize the connection with your database. And you grab your token and your endpoint directly from the Astra UI. And this creates the collection between your app and Astra DB. And then you select which key space you're using, as well as which collection. So we were using the animal collection in our example. And here's where I can actually insert my documents. I grabbed this again from another JSON file that I've had, and notice how my description field here is titled vectorize. So simply just by changing the keyword from what it should look like, which is description, changing that to $vectorize and giving that into our insert statement for our Astra database, it knows to use that field to vectorize and then basically get that vector embedding at the end. So if I go ahead and run this, let's comment this out real quick and run this. You'll see the 3 items that have been inserted should be Samoyed, Serval, and Scottish Terrier. And let's see that reflect here on this side. I can actually do a hybrid search here up top and do Samoyed, and boom, we see that actually appear here within our data set just like that. So Really awesome how quick we're able to do that and through code. Let's do a fun example really quick because we have a little bit of time. I have a minute here. I can do this. I can go into my JSON. Actually, I can go into my table, and then I can grab a vector here, copy that to my clipboard, hop back into my code, and now I can do a search through code here as well. I'll give my query vector here that large embedding that I just grabbed from my UI. And then what's happening here? It creates this result. It does a collection.find, and it's doing a vector search based off of our query vector. So again, it's using the similarity algorithms to find the most similar vectors or results based off of our query vector. And then it should give us some results here in the output. So let's see if we're able to see that here really quickly. And there you have it. So I did my query vector. I think this was a Alaskan Malamute. So let's see what's the most similar to that. We have a fox, we have a poodle, we have a German Shepherd, Australian Shepherd, a beagle. So you're able to see the vectors, search results here via code, as well as how you would in the UI. And that's it for my demo. Let's now hop into the fun part. We'll do the quiz. So, oh, sorry. But before that, let's do a summary. Today, we learned about vectors, how they represent our data. We learned about the challenges in GenAI with traditional databases and why we need a vector database. We introduced a little bit about embeddings and how we use that to store into our vector database as our data for our generative AI applications. And we also did a quick look into Astra DB as a vector database. And hopefully you have a little bit of confidence of getting started with the vector database and thinking about applying that into your generative AI applications. All right, that was a summary. Thank you again for bearing with us. Let's go into the quiz. If you have your phones, you can just use this QR code to scan. But if you're on your computers or laptops, you could join at menti.com and then use this code to get into our quiz. So feel free to join. Actually, give me 1 second. There we go. Okay, so you should be able to join now, everyone. Cool. I'm seeing the thumbs up. I'll give you a few seconds here to get started. And once everyone's in, we will start the quiz. Okay, 5, 4, code not found with the code. I'm not sure why you're getting that, Andrew. Maybe refresh your screen and some people are having issues. Cool. Okay, sweet. Yeah, maybe try this QR code here. Cool. And then I'll give a few more seconds. I will start the quiz in 3. Oh, yeah, it looks like the code did change. Sorry, folks. Yeah, here's the new code. 99583196. Annie just sent it in the chat. All right, 3, 2, 1. Let's start the quiz. Cool, cool. I'll start it now. Answer fast to get more. What was the first animal used in our very first vector example? Was it cat, dog, wolf, or lion? Dog was the correct answer. All
Nice. Good
right.
memory.
Good. It was very close. I know the cat was there as well. Who's in our first place right now? We have the hustler. Sweet. All right. Next question. What is a vector? So this is a definition-based question. Point represented by a single number, the name of a formula, a quantity that cannot be expressed by a single number, or a portal to another universe. 3, 2, 1. Yes, most of you got it right. Awesome. A quantity that cannot be expressed by a single number. Yes, Andrew, it is definitely a portal. A metaphorical portal. Okay, Agent X9, you are now in first. Getting close. All right. What is not a characteristic of a vector database? It handles complex queries. It efficiently stores high-dimensional data. It allows for fast data retrieval and relevant results, or it's limited to only structured data. Yep, and most of you got it. Awesome. I am super happy about that. And who is now in first? We have Sakura. Okay, this is going any way right now. Next question. What is the name of DataStax's vector database? I hope you all know. And I'm going to scold you if you don't know. Just kidding. Oh, okay.
Right.
I'm glad no one picked astronaut DB or AIDV, but okay, you were close. Sweet, but most of you got it right.
Hey, we have a race to first. Oh man.
I know, I know. Let's see. Agent X9 is back on top.
Wow, wow, wow.
Cool. Okay, we have the last two questions here, and then we'll wrap up. True or false, both vectors and embeddings refer to the numerical representation of data. This one could be a little bit tricky. Answer was true. Correct. And then who is at first now? We still have
Oh
Agent
man.
X9. All right. One more question, Agent X9. Let's see if you could keep it up. Okay. And last question. This one's a bit trickier, so please read this one. Blank, support efficiently storing blank, which represents data that captures meaningful information and semantic relationships. So is it vectors support efficiently storing embeddings? Is it embedding efficiently storing vectors? Is it any of the others? And it was the third one. That was a bit tricky. So props to anybody who got that correct. I know with the amount of time it was a bit pressured. So let's see who came out on top. Oh, Tiger
Wow.
Baby with the last minute first
So glad.
place. All right. If Tiger Baby is still here, please leave a comment there so we can get your full first and last name, and we can reach out to you and give you your swag as your prize. Yeah, Tiger Baby, please give us your information, and we'll have our team reach out. And that was it. Thanks for the folks who held on till the end. I know some parts were just a little bit rocky with the technical difficulties. So again, thank you very much. Oh, Claudio, congrats. Awesome. Here are some quick access QR codes and resources for your own convenience. So for Astra DB, as well as more about DataStax, please email Michelle, Claudio, for your swag. Any last remarks?
I thought this was a very great session. It was a blast being with you all, minus the little technical difficulties here and there, but hope that you guys all learned something. And always feel free to reach out if you have any questions, and we're here to try to help out in any way we can.
Yeah, the recording will be shared. Thanks everyone for your participation. It's really quite fun to do these with such an engaged audience, even though we can't see all of y'all. So yeah, I had a blast today. I hope that folks learned things. Yeah, had a great time.
Yes, yes. Echoing off of them again. And apologies again for going over time. You guys have been amazing for bearing with us. Please keep an eye out for the next live stream. And Annie and Eddie, thank you again for joining me today. I hope you all learned something. And yeah, keep a lookout for what DataStax has coming up next to offer. Thank you again. Take care,
Thank you
everyone.
so
Bye bye.
much.